All right, so let me remind you that on Friday, we were asked to make uh, make Taylor and Maclaurin polynomials for a bunch of different functions, but they all kind of had the same format. They were like 1 over some version of x, in that case 1 plus x, there's 1 minus x, here 2 minus x, etc. And the trick for all of those, where can I write it? The trick for all of those were to somehow edit the fact that this function is equal to this geometric series for small enough x's. Remember? So either you would edit what the input was, or you would multiply this by something if you wanted to edit the numerator, or you take the derivative, which is like what we did here in example 4, or like something like that. That was a summary of what we did Friday. And this is a good thing to know. Like, that's one that you should know off the top of your head. And then today you'll look at 3 other ones, e to the x sine of x and cosine of x. 3 other like series that you should know ideally off the top of your head. So that you can do this type of converting back and forth between series and functions. What was I going to say though? Oh, I was going to say that I don't think I said this on Friday, or maybe I did. But for any of these, I don't want to actually do it, but like for any of these, if you wanted to get this series just by taking g of 0, then g prime of 0, then g double prime of 0, and making your polynomial that way, like g of 0 plus that much plus times x plus this much times x squared over 2 factorial, etc. Like, put these values in there, like do it the long way that we did in 10.6, you'd get the same answer or some version of the same answer. But it's just easier, it saves you time if you can use the thing I highlighted down there. This thing. If you can somehow edit this function that you already know off the top of your head, you don't have to go through and get 7,000 derivatives until you see a pattern and generalize it into a sum. Cool. Okay, all that was reminders. But now, here's a new problem. It says get the power series representation for that function, natural log of x. And if we had infinite time, I'd have you think, and one of you or 2 of you would get it and we'd share. But I just want to be done learning today so we can start reviewing this whole week and next week. By the way, speaking of reviewing and using our time good, on Wednesday I don't have a meeting, so I told you this last week, but reminder that on Wednesday I don't have a morning meeting, meaning I'll be here for anybody who wants to come to VC and we can review, because it's getting down to the wire. We have 2 weeks before your test. Okay, but like I said, I think if you thought about this long enough, you'd get the series yourself. But let me show you that the trick is to do this. The trick is, again, I gotta think always really hard, because then I gotta like think about, am I going backwards or forwards and I'm taking derivatives, or am I not? So let me go like this. I know that the derivative of natural log will be helpful, because then at least that'll look like one of the previous problems that we did, with at least there's a fraction in it. So I can incorporate somehow this geometric series into it. Okay, so g prime is equal to this, which I hope you remember. That will be helpful if I write it like 1 minus something. And then if I think real hard, I can say 1 over x is the same thing as 1 minus 1. That gets rid of the 1. And then minus x. So that minus negative becomes the 1 over x. Agreed? Okay, so now I've been talking a long time. Now you tell me, do you remember what the series for this would look like? That function in a series. You guys don't recall? We'll here's a hint, what I just highlighted. If it was just 1 minus normal x, it'd be x to the n. So 1 minus 1 minus x. Is that enough of a hint? Okay, all right. Good. Not just x to the n, but this whole thing to the n. Yeah. Okay. Cool. So there's g prime of x. That doesn't actually help us because we need g of x, but it does help us because we know that if we just take the antiderivative of this, then we would get g of x. In other words, again, if I take the antiderivative of that blue, I would get what I want, so I need to take the antiderivative of its corresponding sum, and I would get the series that goes with natural log of x. Okay, so then let me do that in red. That means that g of x is the antiderivative of 1 over x, which would be the antiderivative of this sum. Okay, and when you see it written out like this and it says integral of an infinite sum and there's x's and n's and dx's, then it looks really scary. But again, if you take the time and you think about how this would just be the antiderivative of, you don't have to write this, but just come into so it doesn't feel like cheating. This would be like the antiderivative of 1 plus 1 minus x plus 1 minus x squared plus blah, 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 like that forever. And so you can see, you can just take the antiderivative term by term, and there's no cheating going on. So what I mean is when you take the antiderivative of this, that's just the same thing as the antiderivative of each term. So you end up getting antiderivative of 1 minus x to the n would be 1 minus x to the n plus 1 over n plus 1. Like, it's just the antiderivative of this. However, I kind of oversimplified because this is 1 minus x. So I don't think I want to get into the super detailed. Wait a second. Yeah, I'm right. I don't think I want to get into the super details of it, but if you want to, you could do some u substitution and get that du would be negative dx. So this should actually be negative this whole thing. I'll just put it here, I guess. Negative that whole thing. And now that should do it. But I've skipped so many steps that I've confused myself. So let me just verify by going to Desmos. But that should be, this series should match that function. But let's check. The only thing is, if you're thinking about the plus c, I got something to say about it in a sec. But for now, let's not worry about it. All right, f of x, well, let me just call it what it was. G of x was natural log of x. Our series was the sum from 0 to infinity, but remember, Desmos can't handle infinity, so let me just go 50 terms, negative 1 minus x to the n plus 1. Ooh. And you can see it matches it really well up to its radius of convergence, like up to its interval of convergence between 2 and 0. Cool. All right. So we did good. What was I going to say? Oh, this asks us get the series and determine its radius of convergence, which is good news. It's not asking us for the interval of convergence. So we know that this dude right here, the original green one that we based our whole series off of, that has a radius of convergence of 1 because that's when this is 1 minus x is less than 1. If you solve that, that has a radius of convergence of 1. So when I take the antiderivative, it also has a radius of convergence of 1. We talked about that Friday. That's why I went through that fast. Cool. Okay. One more thing about this problem, and then we can be done with it, I swear. Is that technically, you know how when I take the antiderivative of this, I will get like natural log of x plus c. That c value, I didn't have you worry about it because I thought you had enough to worry about with the series and the antiderivatives and stuff like that. But you kind of don't have to worry about it because we know that g of 1, which would be the natural log of 1, equals 0. And so if you use this initial condition to get the c value here, look at if I plug in 1 into my series, I get the 0 that I wanted. So basically I'd get this, all this stuff plus c, and then I'd plug in 1 and set it equal to 0, and I'd see that c equals 0. If you didn't follow, then I'll let you do that on your own, but basically I'm saying we're good. That's our answer. We did it. Question?
For other terms where it doesn't equal where it doesn't make it 0, you have to worry about the c then?
Yeah. Yeah, but you won't see this a ton. That's why I'm not super worried about this because you won't see questions this hard in 2 weeks. I think they'll mostly be like more like what you'll see later today in class. Let me see if it's pulled up. Like later today in class where you get like I don't have it pulled up. But like on the AP test, the way I've seen it is when they say f of 0 is this, f prime of 0 is this, f double prime of 0 is this other number. Now make the second degree Taylor polynomial. Now what if you take the derivative? Oh, okay, it's just a quick little derivative that you have to take, or antiderivative that you have to take. You don't have to think about these like, here's a function, now you somehow use what you know to get the series for it. It's usually not that broad, it's usually very specific things you gotta take the derivative. Other questions? Okay, all right. I believe from this point on, or at some point, this gets a lot less abstract. Yeah, look at this. It starts getting a little bit easier after that question. Okay, so remember this series. Let me bring up the next problem. There it is. Okay, this was our series. Whoa, what the heck? Oh, that messed everything up. Okay. There. Okay. All I wanted to do was keep this red series up while we did this example. Because, again, I told you it feels like cheating to just take the antiderivatives of that term by term. Similar thing is going to happen here where you're going to get the answer in 2 seconds and it feels like cheating, but it's not. Because what we got is that red series, natural log, is equal to this series. And so if I want natural log times x squared, then I can just take that series times x squared. And again, that feels like cheating, but it's not. You're allowed to do that. It might change the radius of convergence, but it should, like your series should not be affected by the x squared, other than the radius of convergence. So watch this. Here's what we want to match. So if I just take this series and multiply it by x squared times this, then you can see it matches it very well up to that same radius of convergence. Cool! All right, done with that one. Hopefully you're okay with that. And then Taylor series expansion. You know about this. I don't have to read anything about this to you because this is like what you know from 10.6. How, well, I won't even say. Taylor series is what we've been doing. I'm not sure why it has that box at that particular point. Then it says, determine the Taylor series for f of x equals e to the x about x equals 0. They might as well have talked about the Maclaurin series because the center is x equals 0. Okay, and this one is not so crazy. This one is more like what you know and love. It's just, I think it's a reminder to it's a reminder about this f of x equals e to the x, so that you know it off the top of your head for the rest of the packet. So remember, the way to go about this is to get f of 0, at least for now, f prime of 0, f double prime of 0, see if you can find a pattern, and then generalize the sum. Okay. So f of 0, if I plug in 0 into that, that would be e to the 0, which is 1. Cool. Then f prime of 0 would be the derivative of e to the x is e to the x, and then plug in 0, and you also get 1. And then the second derivative, same thing, and the third derivative, same thing, etc., etc., etc. So every derivative is going to be 1. And so now when I write the like power series expansion of this, it would look like f of x equals constant term plus first derivative times x to the first over 1 factorial plus 1 times x squared over 2 factorial plus 1 times x cubed over 3 factorial plus blah 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 forever. And that's not new. That's what we did when I first even introduced like this idea of approximating functions with polynomials. This is the example that I gave. So that should look a little bit familiar. The only thing is that I think what they would like you to do here is write this at least like a sum, which would look like 1 times x to the n over n factorial, which I see everybody looking up there for. Because that's what that poster up there says as well. But that's how that poster got it. Is by taking out these derivatives. Cool. Okay, now this one is important. Let me tell you, know it off the top of your head. So now you've got the 1 over 1 minus x, which is the geometric series, and then this e to the x, you should know that as well, is the sum of x to the n over n. At some point on this packet, there's a little box that says, here's the 4 that you should know, just so they're summarized in one little place, but just letting you know. This is one that you should know. Okay, so that's e to the x. E to the negative x, I mean, one option you have is take f of 0, f prime of 0, f double prime of 0, etc. Or the other option you have is do no work at all. Do you see how I can get the antiderivative of the, or sorry, not the antiderivative, the Taylor series for this, just without doing any work? Or maybe using the work that I already used. Yeah.
You just, because it's only chooses to negative, but negative's not, yeah.
Yeah, exactly. If this is if this yellow thing is e to the x, then e to the negative x would be that yellow thing with a negative x instead of a normal x. Negative x to the n over n factorial, and boom, there you go, you got your answer. Or if you wanted to, you can make it really clear that this is the same thing as negative 1 to the n times x to the n over n factorial. And then it kind of looks more like what we're used to with alternating series. Cool! You guys happy? You convinced? You learning? Makes sense? Alright, we're going fast because I don't want to leave any problems for tomorrow. Find the Taylor series for that around x equals -4. I don't think this is useful, or like we did this in 10.6, like almost this exact problem. So I don't think this one is worth the time. I think I want to skip this one. Maybe if we have time to come back later. But I'm going to skip it in class. You're welcome to do it on your own if you want to. But it's just going to take forever because this one, I don't see a way to quickly do it. Like take this series and somehow make it about x equals -4 because all the derivatives change when you plug in -4. So I don't want to do that one. I think that one you have to do the long way. Like f of -4, f prime of -4, all that. All right, Maclaurin series for cosine. That one is like, I think you should do it and see where you're at with all these things. So do the same thing, f of 0, f prime of 0, until you find a pattern, and then see if you can write this up. Let me check how much we have left. I'm going to set a timer because it's going to be down the wire. Nice. Nice. Nice, y'all. All right, let me stop this timer then. It seems like people are in good shape. If you needed to check, you probably heard me writing up here. You could have checked on the board that you're getting the right things. The pattern is that f of 0 is 1, then it goes 0, negative 1, 0, 1, 0, negative 1, 0, 1, etc. And so you're only getting the 0th degree, the 2nd degree, the 4th degree. You're only getting the even degrees of this. So that's what your series should have looked like. And if you're trying to write it in sigma notation, then you need to just tell the sigma only include the even terms, and the even terms are just like are like multiples of 2. So the way you write even numbers in general is like x to the 2nd, x to the 4th, etc. would be x to the 2n. And then don't forget that it's also alternating, so it goes positive, negative, positive, negative, positive, negative, like that. So you need to tell your sum to alternate by doing a negative 1 to some power. And then, again, this always makes me think. But if I want the first term, the 0th term, the first term that I plug in, to be positive, then this needs to be to the n. Right? That way it's negative 1 to 0 is positive 1. Okay, boom, to the n over, and then it's over 2 factorial, 4 factorial, etc. So it's over this power factorial, basically. And that's where the poster got their formula from. Hey, Kira. Cool. Convit question?
Poster doesn't have the 2n factorial.
Oh yeah. Well, it does, but it's really faded. But only I can see it. It's like an orange. And look at the signed one as well. But yeah, all of these. I think all these factorials faded off, but it wouldn't make sense for these not to be over something factorial. Like that's how Taylor series are. Hey, good catch. Where are they? Yeah, look at all Taylor series should have some sort of factorial on. All right, sine of x, it's 36, and we have how much left? This, that. It's pretty fast. All right, sine of x, you would do the same thing. So it's worth doing. Here's like a minute for you guys to try to get sine of x. So you can see where the formula comes from. A minute and a half. I'll even write up here if you, but don't look up if you don't need it. All right, there's your minute and a half. Hopefully you got the, I mean, it's the same thing, just off by a little bit as the cosine one. So the pattern still goes 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, etc. But now you have to match different terms. So now you got to look at, I don't get the constant term, I do get the first degree. I don't get the second, I do get the third, don't the fourth, yes, the fifth, etc. So you're only getting the odd terms. And the way you write that in sigma notation would be to say add up from 0 to infinity. Well, it depends where you started. But we started the other one. We've been starting all of these at 0. So traditionally you started at 0, but you'd also be good to start this at 1 if you wanted to. But your answer would look different than mine a little bit. But anyway, I want only the odd terms. So x to the odd powers. The way you write odd powers is like here's even powers 2 to 2n. And then you'd either add 1 or subtract 1, depending on what you started. I started at 0, so when I plug in 0, I'd get 0, x to the 0, and then I want my first term to be 1, so I'd have to add 1 to here. But if you started at 1, you do 2n minus 1. What time is it? 39. Okay, we're good. We'll finish. And then that's over the same power factorial, so 2n plus 1 factorial. And then this one is also alternating positive, negative, positive, negative. So I have to go negative 1 to the, and then I want my first term to be positive, so again to the n power. Cool, so here's another one that you should know off the top of your head. What is that a question?
Yeah. So you made it negative 1 to the n because you want your first power to be positive, but if you plug in 1 for n, it will be negative 1.
Yeah, it depends, but I'm saying where I started my sum was 0. So if I plug in my 0, I get x to the first here, and I get negative 1 to the 0 there, positive x to the 1. But if you guys started your sum at 1, if you want, I'll write it. Or if you started it differently, if you started at 1 to infinity, then yours would look like n plus 1 here and x to the 2n minus 1 here. So So you might see it both ways, but traditionally it's like a little bit like more common to start at 0 all your sums. Question.
They look on that chart, like why is cosine not the +1 and the sine is the +1? See that?
That's what we got too,
No, but
isn't it?
but
Yeah, look at not +1.
Yeah.
And yes. Other cues. All right, let's rush through the rest of this 4 minutes. Look at elementary series, you should know there's the 4 that I was talking about, the geometric, the e to the x, the cosine of x, and the sine of x. You should know all 4 of those. And you'll have 2 weeks to like really get used to it. 2 weeks and 2 periods a day of review to get used to that. All right, it says find the Maclaurin series for sine of x squared. Okay, well if I have sine of x, then I can get sine of x squared. Not by doing the long thing, f of 0, f prime of 0, etc. Don't do that. Just take the sine of x thing, series, that we just agreed was this. There's sine of x. So what do I do to make it sine of x squared? Yeah, just change the x to x squared. Boop. Done. I got it. Again, feels like cheating, but it's not. And imagine like doing this by hand would take so long to take f of 0, f prime of 0, etc. because you'd get chain rules, then product rules with chain rules, etc. So you don't want to do that. That's why it's good to just know these off the top of your head. So that one, done. We did it. Question.
What's a general term for it?
Find the first 4 non-zero terms in the general term. This would be the general term with the n's in it. The first 4 terms, I didn't read the question, sorry. The first 4 terms would be let's plug in 0, 1, 2, and 3, and that's my first 4 terms. Okay, so let's do it. Plug in 0, I get 1 times x squared to the 1 over 1 factorial. So it'd be just x squared. Plug in 1, I get minus x squared cubed, which would be x to the 6 over 3 factorial. Am I doing too much math in my brain? I just plugged in 0 to all these ends. And I plugged in 1 into all these ends. And I'm about to plug in 2, yes?
Can you use like the one up there? Just plug in X.
Yeah, sure, if you want. But yes. But you won't have that on the AP test, but yes, you could do that right now. Alright, here's me plugging in 2. That would be positive 1. 2 would give me 5 up here, so x squared to the 5 would be x to the 10 over 5 factorial, and now I see the pattern is these are going up by 4, and these are just the odd numbers. Cool! Alright, next one, we're running out of time. Find the Maclaurin series for x times cosine of x. I won't find the first 4 terms. Just because, like, I know that you guys can handle that. But if this was cosine of x, then x times cosine of x is just this times another x. Boom, I'm done. Or if you wanted to, you could take x times x to the 2n and make it an x to the 2n plus 1. But I don't have time to show you. And then last one, you guys, of your whole high school math, well, some of you, your whole high school math career. It says, find the sum of the series. What on earth? What the heck? Do you guys see what that's going to add up to? Yeah, it's not obvious at first, but let me point something out. 45. Let me point something out. That's all I'll say. Now do you see what it's equal to?
Yeah.
Okay. All right. Well, I don't want you to write stuff down just to write stuff down. So we'll do these last three. They're like a minute long. So we'll do these last three tomorrow. Again, we'll be here Wednesday. So these three tomorrow, then start review right after. All right, we can be done though. We'll finish this tomorrow. Good job, you guys.